So we're looking at membrane transport part 3, and we're focusing here on explaining how a difference in solute concentration across the membrane can cause the movement of water, and explain the distinction between osmolarity and tonicity of a solution. So we'll look at what some of those terms mean and how they differ. Let's first start by describing the definition of osmosis. So we've talked a bit about movement of solutes, movement of particles, and the cell membrane, and how those particles can move across the membrane, the various forces that are acting on those particles to move them across the membrane. But we haven't really talked too much about water and how water moves across the membrane. So osmosis, by definition, is diffusion of water through a membrane. The characteristics that define osmosis are that it is always passive. So it's always going to be moving from high concentration of water, that is, to low concentration of water, or down the concentration gradient of water, or passive or spontaneous. It is unaffected by the membrane potential. So any charge that exists, it's unaffected by the membrane potential of the cell. It's unaffected by any charged particles. It's unaffected by any electrical driving forces that are moving particles across the membrane, right? Remember, the electrical forces are only acting on charged particles. So when we speak about the membrane potential and the electrical driving force, we're really only looking at solutes that have a charge, sodium, potassium, etc. So water, being uncharged, is completely unaffected by the membrane potential. And then thirdly, it is driven by the water gradient. And interestingly, we want to think about the water gradient as being opposite of the solute gradient. So if we look at these two scenarios on the right here, we can think about scenario A. There is a high water concentration outside of the cell, and then a lower water concentration inside the cell because we have solutes dissolved in the solution inside the cell. So because we have pure water on the outside, right, we have 0 moles in terms of the solute concentration, 55.5 moles in terms of the water concentration. So this is pure water. And inside the cell, we have 0.3 moles of solutes dissolved, giving us an osmolarity of 300 milliosmoles. And the water concentration is 55.2 moles, right? Because we've displaced some of that water by having solutes inside. So we have a slightly lower water concentration. So given that, our gradient is higher water concentration outside, lower water concentration inside. So the direction that water is going to move passively is the outside of the cell to the inside of the cell. Now, another way to reframe that and look at that is thinking about the solute concentration. Water is going to move against the solute concentration gradient. So because I have a lot of solutes inside the cell and no solutes outside the cell, water is moving from a place of low solute concentration to high solute concentration. So we can think about osmosis as being in the direction of the water gradient or in the opposite direction of the solute gradient, okay? Looking at the scenario B, let's look at another example. So down here we have sucrose, right? We have 1,000 milliosmol as the osmolarity of the solution outside, and then the water concentration is 54.5 moles of water, right? So it's not pure water. It has some solutes, i.e. sucrose, dissolved in the solution. And on the inside of our cell, we have solute concentration as well. 300 is the osmolarity, so it's a lower amount of solute concentration. And then the solution for water is 55.2 moles of water. So the concentration for water is going to be higher on the inside of the cell and lower on the outside of the cell. So if we think about our gradient here again, water is moving from high concentration of water inside the cell to a low concentration outside the cell. Or if we look at the solute concentration, water is moving from a low solute concentration, our osmolarity here is 300 milliosmoles, to a high solute concentration, our osmolarity outside the cell being much higher. Okay, so two ways to think about the direction of water movement by osmosis. Let's look at what the osmolarity means. We've used that term a little bit here. Let's talk about what the osmolarity means and how that's different from the concentration, which is the moles. Now, the osmolarity is the total solute concentration dissolved in a solution of fluid. Okay, it's the total number of solute particles that are displaced in that water solution. And this is how it differs from just looking at the moles. The moles is just the solutes. If I have 0.1 mole of glucose, that's just the solids. It's not displaced in any water. It's not displaced in any solution, just the pure solute particles. If I were to put that 0.1 mole of glucose into a liter of water, now I have a solution with an osmolarity of 0.1 osmoles of solution. Okay, that is now the osmolarity for the combined solution. If I looked at a different type of solute particle like sodium chloride, and I have 0.1 moles of sodium chloride not displaced in any water, and I do put that 0.1 mole of sodium chloride into a liter of water, the osmolarity here is going to be higher because now I have two solute particles that are going to be displaced in that 1 liter of solution, right? Because now sodium is going to be displaced, 0.1 mole of sodium displaces, 0.1 mole of chloride displaces, and now I have a total combined osmolarity of 0.2 in that liter of water. So we give this example to say that the total number of solids that are dissolved is what reflects the osmolarity. And so if I have a compound that is going to further dissociate into separate solute particles, that is going to impact the overall osmolarity. Now, in terms of our physiology, the units that we use are milliosmoles. This is 1,000th of an osmole, just because in our physiology, the osmolarity is much lower in terms of the number of solute particles dissolved in our plasma, etc. Okay, so it's by the milliosmole or 1,000th of an osmole. And having said that, if we look at our fluid compartments, intracellular, extracellular, the osmolarity is 300 milliosmoles, which tells us that there are 3 in 1,000, right, particles dissolved in our fluid compartments, right? So very minute amount of solutes or particles dissolved in our extracellular fluid, intracellular fluid, plasma, etc. Okay, and so this is the number that we want to strive to be at as we think about things like homeostasis. If we have excess water inserted into our fluid compartments, that can dissolve the osmolarity of our fluids. If we have excess water removed from our fluid compartments, that can also manipulate or sort of condense or saturate the osmolarity of our fluid compartments. So that can lead to dangerous consequences, which I'll talk about coming up. So where we want to be, the set point that we are striving to be at in terms of the osmolarity of our fluid is 300 milliosmoles. Okay. Now, based on that, we can think about differing solutions. So a hyperosmotic solution versus an isoosmotic solution versus an hypoosmotic solution. So hyper, iso, and hypo. What does that mean? That means that we're having different osmolarities as compared to the cell or the fluid inside the cell. So in this scenario, we have an animal cell, which is like our cell. And if we insert that cell into a hyperosmotic solution, this means that there are more solute particles dissolved than exist within our intracellular fluid. So what this means is the cell is going to release water into that hyperosmotic solution because now we have a fluid gradient. Ideally, in our cells, this should be an isoosmotic situation where there's movement of water from one direction to the other, but there's no net flux or net accumulation of water on either side. So in the hyperosmotic example here, water leaves the cell shrivels up, and the cell dies. Okay, if we kind of think about the clinical picture of what this looks like, this is going to lead to dehydration. And dehydration means that we're going to see a lot of water leaving our cells. The way that this shows up in terms of clinical symptoms is there can be fatigue, there can be severe dehydration, there can be lethargy, there can be decreased urine output, and that can lead to kidney failure and lots of other consequences as well. So we definitely want to make sure that all of the cells in our body are exposed to a fluid that is the same osmolarity as our cells, which is 300 milliosmoles. On the other end of the spectrum, if we have a solution that is hypoosmotic as compared to the osmolarity of our cells, we're going to see the opposite phenomena occur. We're going to see water move from the fluid because we have a higher water concentration, fewer solutes dissolved, and that water gradient now favors water moving into the cell where there is a lower water concentration. So water moves into the cell swells, and the cell ruptures or lyses and also dies. Okay, so again, dangerous for our cells to be exposed to either hyperosmotic or hypoosmotic solutions. It should be isoosmotic solutions. And in the case of the hypoosmotic solutions, just a practical example of this is water intoxication. So if we, for example, were to inject water, right, pure straight water into our veins as opposed to saline, which has an osmolarity that's close to our cells, if we were to inject water into our veins, this is what would happen. Cells would lyse, they would rupture, they would die. This would lead to seizures. This would lead to altered mental status, confusion. This would lead to coma, right? So very, very dangerous for our cells to be exposed to pure water or even hyperosmotic solutions, which are have a higher osmolarity than our cells. Okay, let's talk about osmotic pressure and the osmotic pressure gradient. So what do we mean by osmotic pressure? This is a reflection of the solute concentration and the ability of the solute concentration to pull water towards it. Okay, this is why I think it's really interesting to think about the direction of water movement, not just in terms of the water gradient, but think about it in the opposite in terms of the solute gradient. Because if we have two scenarios here, right, we have side one, side two. Side one has more water dissolved, has a higher water concentration and a lower solute concentration. Okay, side two has the opposite. It has a higher solute concentration and a lower water concentration. So we can think about side two as exerting an osmotic pull. This is what we refer to as being the osmotic pressure. It's the ability of the side that has the higher solute concentration and the lower water concentration to exert an osmotic pressure or an osmotic pull that actually draws the water to that side. In terms of the units that we can use to measure that force, right, that pulling pressure can be expressed as a force or a pressure, and the units that we use are atmospheres, right, just like with any other force, like gravity or so. So we can think about side one as having a lower osmotic pressure, 7.4 atmospheres, and side two as having a higher or stronger osmotic pressure at 12.3 atmospheres. All right. Now we can also calculate the gradient, the osmotic pressure gradient, which tells us that side one has a lower pressure, side two has a higher pressure. So the direction of our gradient is going to be from the lower osmotic pressure towards the higher osmotic pressure, which is going to be from side one to side two. And the strength or magnitude of that force is going to be the differential, which is about 4.9 atmospheres. Okay, so 4.9 atmospheres is the pressure that is exerted from side two onto side one to pull water from side one to side two. Okay, another way that we can express this force is what is the pressure that would need to be applied in order to stop or halt that water movement? And that can also be expressed as that 4.9 atmospheres. That is, if we exerted a force on side one that was 4.9 atmospheres, we would stop the water flow towards side two. Okay, So different ways to look at the way that water can move and the pressure or force that can be exerted by that movement. All right, let's get to talking about tonicity. Tonicity is another term that is used when we think about water and the gradient that's created by water movement. So the definition of tonicity is the water gradient that is caused by the impermeant solutes. So with tonicity, we're not looking at all the solutes that are dissolved in either solution. We're looking at only the impermeant solutes, so only the solute particles that cannot cross the membrane. So osmolarity takes into account all of the solutes dissolved. Tonicity takes into account only the solutes that cannot move across the membrane. All right. And in the example here, we can think about a hypertonic solution, which is, a hypotonic solution, which is where the tonicity is lower, so water enters the cell. Isotonic solution, which is where the tonicity is the same, so it stays the same, and a hypertonic solution, which is greater than the tonicity of the solution, and that is where water leaves the cell, and then it's going to shrivel. So it's a similar phenomena in terms of hyper, iso, and hyper, but the difference is that we're only looking at solutes that cannot cross the membrane. Let's look at an example and help illustrate what that means. So how do we differentiate osmolarity and tonicity? Now, in the example here on the left, we're looking at the osmolarity, right? We're looking at all the solutes dissolved. So if we take all of the solutes dissolved into account, outside of the cell, we have urea dissolved. So this 300 milliosmol is the osmolarity of the solution outside the cell. 300 milliosmol is the solution inside the cell as well. So in this instance, we can think about this as being an isoosmotic scenario, right? Both of these solutions have the same osmolarity. The only difference is the particle urea cannot move across the membrane, okay? The particle urea can move across the membrane, and the particle in purple, the impermeant solute, cannot move across the membrane. But in terms of osmolarity, we're looking at both of the particles, whether they can move or not. If we think about the tonicity, however, the tonicity here differs because we're only honoring the particles in purple that cannot move across the membrane when we look at tonicity. So in this instance, we have urea being able to move. So urea can move to get to a steady state where the solute particles on either side is the same. However, the particle in purple, the impermeant solute, cannot move. So the tonicity is going to be in favor of only looking at the particle in purple. So having said that, we now have pure water on the outside because we're completely ignoring urea when we think about tonicity. Pure water on the outside, and then a higher osmolarity with the solute purple on the inside. So while we think about the solution as being isoosmotic here, if we think about the tonicity, it's actually hypotonic, okay? So isoosmotic because we're looking at both solutes in this case, hypotonic because we're completely ignoring urea because it can move across the membrane, okay? All right, any questions on this bit? Osmolarity versus tonicity, any questions? All right, okay. So here's just another table just comparing the differences between osmolarity and tonicity. Again, osmolarity, looking at the total solute concentration, both permeant and impermeant. Tonicity, looking at only the impermeant solutes relative to the intracellular fluid or the cell osmolarity. Okay, now here are just some more examples to look at the direction of water movement. So in the scenario A, we have a high osmolarity inside the cell, a low osmolarity outside the cell. And as you would imagine, the water is going to move from the outside of the cell, where we have higher water concentration, to the inside of the cell where we have a lower water concentration until both solutions are isoosmotic. Okay. In scenario B, we're going to see the opposite. We have a high solute concentration outside the cell, low solute concentration inside the cell, which means we have a higher water inside the cell, lower water outside the cell. And in terms of the direction of movement of water, it's going to be from the inside of the cell to the outside of the cell, which means that we're going to see the movement until both solutions are going to be the same osmolarity. Okay, so again, two ways to look at that. Water moving from high water concentration to low water concentration, or solutes moving from low solute concentration, or water moving from low solute concentration, again, inside the cell, to high solute concentration outside the cell.